This is a video about center of mass. The center of mass is something that we've actually been using quite a bit without really talking about it. The idea here is there is a location on an object or on a collection of objects that is the center. If we reduce the object to a single point, like we do with free body diagrams, we are reducing it to a point that exists at the center of mass of the object. So what this looks like, there are some easy examples. If I've got a particle like this, and I've got a particle like this, I can find the center of mass of the system. Now if these are equal masses, then the center of mass is going to be right here in the middle. It's just kind of the balance point. If they're not, then I need to be able to come up with something. So let's give this thing a coordinate axis that passes right through that first point. We'll say this is our y-axis, this is our x-axis, and we're going to try and find a center of mass. This is D. The center of mass equation, I will tell you, looks a little bit daunting. We say the x component of the center of mass is going to be the sum of xi mi over the sum of mi. And that doesn't look great, so let's try that. This is x1 m1 plus x2 m2. If we had more of them, we would have more, divided by m1 plus m2 plus however many masses we've got. So that already looks less awful than this. But we should see what this looks like. In this case, we would have, and let me give this thing some numbers. We'll go 10 kilograms. We'll call this one 20 kilograms. And we'll call this a distance of 12 meters. So this would be, we know that the balance point is going to end up being closer to the 20 than it is to the 10. If I had a very lightweight stick and I put a block on this end and I put a bigger, heavier block on this end, and I told you hold this up with one hand, you're going to put your hand over here somewhere so that it balances. That's what we're actually finding here. So I'm going to say x1 times m1, so 0 times 10 kilograms plus x2, which is 12 meters, times 20 kilograms, divided by m1 plus m2. 0 times 10, that's 0. 12 times 20 is 240. 240 divided by 30, so 240 kilogram meters divided by 30 kilograms is the same as 24 divided by 3, that is 8. Kilograms and kilograms drop and I'm left with 8 meters. This whole distance is 12 meters, that puts me, this would be 6, so that puts me here, about 2/3 of the way down the line. Which makes sense because 2/3 of my mass is down at the far end. That's how I'm finding center of mass. That's the basic idea. If I want to find the y coordinate, I'm going to do the same thing with the y's. y1 m1 plus y2 m2 over m1 plus m2, but that's 0, that's 0. I'm going to get 0, and it wouldn't make sense any other way. The balance point couldn't be up here. There's just nothing up there to balance it. If I did have more particles, I would just keep adding more in. So if I had a particle here, a particle here, and a particle here, and maybe these are 1 kilogram, 2 kilograms, 3 kilograms, I can draw an axis, and I can look. Horizontally, I have 3 kilograms on this line, 3 kilograms on this line. I expect I know that my x-coordinate for my center of mass is going to be right there at the midpoint. Vertically, I have 2 kilograms up here. I have 4 kilograms down on this line. So if this is if this is like the halfway point between those, I know I'm going to have to be here, below that. So I expect my center of mass of this system to be right around there. I didn't give you any kind of values or scales or anything like that. I'm just saying kind of qualitatively you can see where that's going to be. We should also talk about whole shapes. If I have a shape like a box, and maybe this thing has a width of W and a height of H, we can think of this box as being made of a bunch of tiny boxes, if you like, and we can do it that way. But what we're going to find is that there are exactly as many tiny boxes on the left side as there would be on the right. There are exactly as many on the top as there would be on the bottom, and the center of mass of a geometric shape that's equally weighed, which is what we're going to worry about in a trig-based class. If you were taking a calc-based class, then you would have to start looking at different mass distributions and functions, because calculus makes it so that you can do those things. When that's not the case, when we are looking not in a calc-based class, we are going to have a uniform mass distribution. Uniform mass distribution really just means if I've got this box, any spot that I cut a little piece out of that box will have the same mass. If I cut a little piece out of this side or a little piece out of this side, if it's all made of the same material, that's going to be the case. If I had a box instead that was, say, made of steel on the left side and made of foam on the right side, that would not be a uniform mass distribution. So uniform mass distribution for a box, my center of mass is going to be right in the middle of that box. For a circle, let's try that again. For a circle, my center of mass is going to be in the center of that circle. No surprises there. So for any symmetric shape, my center of mass is going to be in the middle of that shape. If I have a right triangle, then I start to get something where I don't have a symmetric shape. And now I'm going to need a little bit more. So give this thing a height H, give this thing a width W. What we find is that the center of mass is right here. At this point, where this is H over 3 as measured from my right angle, and this is W over 3 as measured from my right angle. That's it. We don't really need to get into more complicated shapes than that. Rectangles, circles, triangles, those are where we're going to be living.